We have so far been primarily focused on the internal energy, but there are other important state functions that we will use, and which we will use more heavily in this class. And so let's consider how we can arrive at the differential forms of those state functions as well. So we started out with the internal energy U. We have already seen that there is another state function H, which is the enthalpy, and which we defined as U plus PV. Another useful state function is F, the Helmholtz free energy, sometimes known as A. We're going to call it F, though, so as to not sort of confuse it with A, which might be area, but which we will also use as affinity. So the Helmholtz free energy is defined as U minus Ts, and the one that we will in the end use most often in here is the Gibbs free energy, which is defined as U plus PV minus Ts. So let's look at an example of how we arrive at the differential form for one of these. And we will use our example. So we have F is defined as U minus Ts. F is a state function, so we can write dF as du minus dTs, and we can expand that to say TdS minus SDT. So this is dF. Now we are going to substitute in for du the combined first and second laws. So we're going to say that this is TdS minus PdV, and then keep what we have here. Now you can see that we have here TdS, and here we have minus TdS, and so those two terms cancel each other, and we are left with dF equals minus PdV minus SDT. And if we have any other work terms, we could add those on at the end. So this right here, this is the differential form of the Helmholtz free energy. We can see from this that F is a function of V and T. So you'll notice that we had U, which was a function of V and S, basically, and so we've managed to switch from S to T. And the way we did that was by subtracting off this pair. If it turns out if you have an isothermal process, this term here goes to 0, and dF is just equal to minus PdV plus any other work, and so sometimes the Helmholtz free energy is called the work function. So this is an example of how we have arrived at the differential form of another state function and can then sort of extract the variables of which it is a function.